In this online lecture, we're going to discuss the color and magnetism for transition metal complexes. First, we need to do a broader overview of color. What is color? And what are the mechanisms of color? How do we see color? After our discussion of color, we'll segue over to how we can use crystal field theory to predict color. And we'll also talk about charge transfer events in transition metal complexes, which also cause our complexes to be colorful. And finally, we'll talk about magnetism of coordination complexes. So first, I want you to think back to Gen Chem 1. What is light? So pause this video for a second and write down, what is light? So hopefully you remembered that light is a wave. Well, it's both a wave and a particle, but it's a wave that is the periodic variation of an electric field. We also call it electromagnetic radiation. There are a lot of different types of electromagnetic radiation. We have very short wavelengths like our X-rays, gamma rays, and cosmic rays. We have longer wavelengths such as our microwaves and our radio waves. And here in the middle, we have visible light. So it's a very small portion of our electromagnetic spectrum. From 400 nanometers to 700 nanometers, we have from violet to red visible light. So visible light is light that we can see. And when all visible light is added together, when you mix all of these different wavelengths together, you get white light. But if white light can be separated in a variety of different mechanisms, which we will talk about, we will see color. Okay, so how do we see color? I just mentioned that we have to separate white light. So I want you to think about that for a minute. What are some of the different ways that we can separate out white light or generate specific wavelengths of light to see color? So there's a few different ways that we see specific colors. The first is emission. So if you remember back to Gen Chem 1, one of the labs that you did was looking at the emission spectra for several different gases. This one's neon. Neon glows red. And this is because it's emitting a few different wavelengths of light that when they add together, they give this vibrant red color. We also have interference. So these are some niobium earrings, but interference you also see in oil slicks, on bubbles. This is when your light constructively and deconstructively interferes so that we see specific colors. We also have absorption and reflection / transmission. This is probably what we most commonly think of when we think of mechanisms that create color. So transition metal complexes that are colored are typically absorbing some visible light, such as this example where your green and yellow light is absorbed, and then your purple, blue, orange, and red are all transmitted so that when these different colors add together, this additive mixing of light, we see this pink color. And then the last color mechanism is dispersion. Dispersion is when we are separating out our white light into the individual colors. Before we can talk about each one of these mechanisms, we need to talk about one more concept, and that is resonance. So I want you to pause this video and think for a couple minutes and write this down. What is a definition of resonance? Remember that we're specifically talking about resonance in the context of light and color. So there's a few different contexts where we talk about resonance, but we're specifically talking about this in the context of color and light. So energy is quantized. This is a really important concept from quantum mechanics. Remember, we had the Bohr model. The Bohr model was able to describe the emission spectra that we saw for hydrogen. And the Bohr model said that we had these quantized energy levels for hydrogen, these shells, n equals 1, 2, and 3. You can think of them like stairs. So the energy for hydrogen can only exist on these specific levels or on these stairs. So resonance is this concept where your energy of a photon that's coming in is exactly equal to this energy separation, delta E, between these two energy levels. And when this happens, we get an excitation. So this is called resonance. So light can be absorbed when resonance is achieved. So this compound won't absorb just any light. It will only absorb light with a specific energy that can create this excitation. So there's a song called Sober Up by AJR. And in that song, there's a line that says, "My favorite color is you. You're vibrating at my frequency." So I heard this song and I was like, that's resonance. So this is resonance as explained by AJR. So this is an indigo molecule, for example, and indigo absorbs orange and yellow wavelengths of light and red and reflects back our blues and purples. For indigo, it's specifically orange light that can create this excitation from the ground state to the excited state. So this is resonance, when that photon of light is equal to that energy difference between that ground state and that excited state. When this resonance condition occurs, then you can have excitation and absorption of light. Emission is also a resonance condition, except it's resonance condition in the opposite direction. In the example of our neon lamp, we're running an electrical charge through this neon lamp. And so we're exciting all of the electrons into these higher energy states. And when the electron relaxes back down to the ground state, then a photon of light is emitted, and the energy of that photon is exactly equal to the energy difference from the excited state to the ground state. So this is resonance. But we can also see atomic emission for metallic salts, not just gases. So this is the flame test. It's the same concept. You have these different metals that when you excite them with a flame in this example, the electrons are excited to higher energy states, and when they relax back down, they emit these colors. So we get different emission spectra for different metals, and we can get these different colors. And these are some birthday candles that I bought from King Soopers that work based on atomic emission. Okay, I mentioned that interference was also a mechanism for color. So a couple examples of interference in nature are a lot of the morpho butterfly wings. This blue color isn't a result of absorption of light. It's actually a result of interference. Bubbles, the color on bubbles are from interference, and peacock feathers, shells, iridescent opals, they're all examples of interference in nature. When your light hits your bubble, it reflects, and the angle that it reflects depends on the thickness of the bubble. When these waves reflect off at slightly different angles, they will constructively and deconstructively interfere. So when waves are in phase, they'll constructively interfere, and when they are out of phase, they will deconstructively interfere. So when those different colors are constructively and deconstructively interfering, we no longer have all of the colors that make up white light, and we see color. Another example of interference, these niobium earrings. So this is from my chemistry and art class. So niobium you can oxidize, and when you oxidize niobium, depending upon the thickness of that niobium oxide layer, again, you can get interference of light that causes light to constructively and deconstructively interfere to see color. Okay, absorption and reflection. This is probably what we often think about with color. White light is hitting an object, and that object is absorbing some colors, and then it's reflecting off the color that we see. Okay, so we often, when we're talking about color, we're typically talking about what's called electronic transitions. So the excitation of electrons. And for transition metal complexes, there's two different types of electronic transitions that we often will see. One is called a D to D transition, and the other is a charge transfer. A D to D transition takes place when you have partially filled d orbitals, and absorption occurs when the energy of the photon that's coming in, so when you have a photon of light that's coming in when the energy of that photon is equal to delta octahedral, then we have the exact energy to excite from the T2G into the EG orbital. So this is what's called a D to D transition. You're going from the T2G to the EG when your energy of your photon is exactly equal to this energy separation delta octahedral. And remember that your energy of your photon is equal to hc over lambda. So as delta octahedral increases, your wavelength is going to decrease. That's going to be absorbed. We also can have charge transfer events. So a photon can excite an electron from a ligand to a metal, or from a metal to a ligand in a transition metal complex. This is a cyanotype. This cyanotype is colored because of a charge transfer, actually from two metal centers, but we'll often see charge transfers from ligands to metals or metals to ligands. Okay, so just to review again, remind you what an electronic transition is. So this again is a very crude Bohr model. That electron can absorb energy. So here's white light, and white light has a bunch of different wavelengths. And the specific wavelength that has the correct energy for this energy difference will excite an electron from the ground to an excited state. And then the other wavelengths of light that are not absorbed will be transmitted, and we will see color. Okay, D to D transitions again. This is the transition between different d orbitals. So you have to have a compound with a transition metal with unfilled d orbitals for a D to D transition to take place. This is hexaaqua titanium 3. If you look on the periodic table, titanium 3 is in the 4th group. So it has a D1 electron configuration. So this electron in our T2G orbital can be excited up to the EG orbital if we have a photon that comes in and the energy of that photon is exactly equal to this energy difference, which is delta octahedral. So in this case, delta octahedral corresponds to a green and yellow wavelength to excite this electron, and then we transmit these red, orange, blue, and purple, and these colors of light will add together, additive mixing, so that we will see this pink color when we look at this titanium complex. This is the same complex, just another figure of what the absorption spectrum looks like. We can see that the lambda max is at 490 nanometers. So we could actually calculate. So this is our resonance condition. So this wavelength is equal to Planck's constant times the speed of light divided by delta octahedral, or we could calculate what delta octahedral is based on this wavelength. Here's just a few different transition metal complexes: titanium 3, chromium 3, manganese 2, iron 3, cobalt 2, nickel 2, and copper 2. And so you can see the different colors of these transition metal complexes. Okay, coming back to this figure of the titanium, we can actually use this color wheel to make predictions about what the color is going to be. So remember that we said that this lambda max was around 490 nanometers. So we can look on this color wheel and we can see, oh, 490 is a green wavelength. So if we're absorbing green, we can make predictions that this is going to be, so we're absorbing sort of, it's a band, so it's multiple wavelengths that are being absorbed. We're absorbing in the green, yellow, and what we're transmitting is in the red, violet. So you're going to observe the color on the opposite side of the color wheel from what is absorbed. And remember the factors that affect our delta octahedral. So differences in delta octahedral will cause different wavelengths of light to be absorbed. And the biggest thing that we'll look at here is our spectrochemical series, weak field versus strong field ligands. And remember that we talked about pi back bonding, and this is the reason why your cyano and carbonyl ligands are strong field ligands. So here's an example where chromium is the metal center for all of these different solutions. Each of these are D3. So we're going to have 3 unpaired electrons regardless of the size of our delta octahedral. But what we can see here is that our weak field ligand, hexafluorochromium 3+, is a green color. And so that means that it's absorbing in the red region. So we could say, okay, maybe lambda max is around 700 nanometers. For this hexaquachromium plus, we have a purple color. So that means we're probably absorbing somewhere in the yellow region. So we could say, okay, lambda max is probably around 570 nanometers. And then our chromium, our hexaamine and hexacyano are both yellow. So that means that these are absorbing somewhere in the violet. And then this one's probably blue/violet region. So this would be a lambda max of, somewhere around 430 nanometers, and this one might be around 400 nanometers. As delta octahedral is increasing, we're absorbing shorter and shorter wavelengths of light, which is resulting in different colors. So as chromium goes from being attached to a weak field ligand to a strong field ligand, delta octahedral increases, and the color of the complex changes from green to yellow. Okay, here's just the actual colors of 2 of the complexes that were in this previous example. So hexa-aqua is this bluish purple color. It's absorbing somewhere in this orange yellow, and then hexaamine chromium 3 is yellow, so it's absorbing somewhere in the blue violet. And again, amine is a strong field ligand, aqua is an intermediate, but it's a weaker field ligand. We also will have situations where our transition metal complexes will be colorless. And there's a few reasons for this. The first is a D10 electron configuration. So zinc 2+, for example, has a D10 electron configuration. All of these orbitals are completely filled. And so what that means is that there's no place for an electron to be excited from the T2G to the EG sublevel. And so this means that you can't there's no D to D transition. So there's no way for an electron to be excited into this EG sublevel. So here is zinc 2+ in water, and you can see it's colorless. And here's another example, manganese 2+. This is D5. And we're going to assume that this is a high spin case because water's an intermediate ligand and manganese is small. So this is D5 high spin. So that means you have an unpaired electron in each one of these orbitals. And so what's happening here is because all of these electrons are all spin up, to excite an electron from the T2G to the EG orbital, we'd have to have a spin flip, which is a forbidden transition. So that's why this manganese complex is almost clear. You can see that it's faintly pink. So a few of these transitions will take place, but not very many. Okay, so I wanted to just talk about, in general, a few different pigments that contain different metals. So malachite and azurite both contain copper. Vermilion contains mercury. Yellow ochre, red ochre, there's actually a lot of different iron pigments, iron-based pigments. Prussian blue, cobalt blue contains cobalt, obviously, and then chrome, oxide green, chrome yellow, those all contain chromium. So there are many, many pigments that we use in painting and in art that contain different metals. So there's another type of mechanism for color besides D to D transitions, and those are charge transfer transitions. Electronic transitions that occur between an anion and a cation in inorganic compounds, and it could be between actually two cations. They don't have to be a positive and a negative, but typically they have pretty intense absorption bands in the UV invisible range, so they often absorb more intensely than D to D transitions. So for transition metal complexes, we'll often see an electron transfer between a metal ion and a ligand, or from a ligand to a metal. We call these ligand to metal charge transfers or metal to ligand. So what you can imagine is you have your sigma orbitals from your ligands, and if you have, say, an empty Eg orbital on your metal, you can have a charge transfer from your ligand to your metal Eg orbital. So this is a ligand to metal charge transfer. You could also imagine a situation where you have empty antibonding orbitals on your ligands, and you could get excitation from your metal to your ligand. So this is a metal to ligand charge transfer, and this is a ligand to metal charge transfer. So both of these charge transfer events are very common with transition metal complexes as well. And I just wanted to mention for pigments, cadmium yellow, vermilion, Prussian blue, all of these are charge transfer mechanisms for color. So let's talk about Prussian blue, discovered by Sir John Herschel in 1842. So you create this complex that has an iron 3 and an iron 2 when exposed to light. And this is also known as a blueprint. So cyanotypes are also blueprints. It's also called ferroprussiate. And just a quick overview on what the cyanotype process is you have a piece of paper, you apply a solution of potassium ferricyanide and ferric ammonium citrate. It's sort of this yellowish color. And then you put some type of resist on it. So maybe a negative, or it could be a flower, and you expose it to light. And then when you expose it to light, what's exposed to light turns this deep blue color. And then you are able to wash off your unreacted iron just with water to get your cyanotype. So this was the first way that people made photocopies, was with this cyanotype or this blueprint process. But again, it's a charge transfer event between these two metal centers that's creating this deep blue color. Okay, we also need to talk about the magnetic moment for transition metal complexes. So magnetic moment is related to how many unpaired electrons are on a transition metal complex. And the way that we can measure this in a lab setting is with an instrument called a Gouy balance. So the amount that this magnet attracts the sample is measured as a difference in weight. And from that, we can calculate the magnetic susceptibility. In this class, we're just going to refer to the magnetic moment. So the magnetic moment is equal to the square root of n times n plus 2, where n is your number of unpaired electrons. So this is what we call the spin-only magnetic moment, times mu sub b, which is the Bohr magneton, which is the magnetic moment for a single electron. So it's typically written as mu over mu sub b. Or sometimes it's written just in mu sub b units. So here's an example using magnetic moments. How can we distinguish between these two solutions? So let's just say that we knew that one was zinc and one was manganese, but we forgot to label these. Well, what we could do, we could write out the crystal field splitting for both of these. And we would find that, okay, this zinc 2 plus is diamagnetic, whereas your manganese 2 plus has 5 unpaired electrons, which would give you a magnetic moment of 5.9 mu sub B. So we have a much bigger magnetic moment for our manganese than we do our zinc. So we could distinguish between the two based on our magnetic moments. Okay, so crystal field theory is awesome because we can use it to make predictions about color and magnetism for coordination complexes.